Hello, we are Group 2 from Tutorial 2, and this is the final presentation for instrumentations and measurements. Our team has developed a pill sorter that has a wide application in market and the industry. Our team has developed a system that can identify and sort given pills based on the size, shape, color, and weight. The need for this project stems from the increasing number of prescription medication that has been observed over the last few years. A study completed in 2011 revealed that approximately 30% of individuals aged between 65 and 79 are taking more than 5 prescribed drugs. Another study in 2018, completed by the Canadian Institute for Health Information, claims that 1 in 4 Canadians in the same age group have more than 10 pills prescribed to their weekly routine. Therefore, our team has developed a system that can accurately sort between the different medications and sort them in specific containers as the continuously aging Canadian population develops bragnesia and poor eyesight, or neurodegenerative diseases such as dementia and Alzheimer's. Moreover, our system is able to determine the mass of pills and identify their purity for the substance that is produced by pharmaceutical companies and therefore can be applied to the industrial environment.
In this section, we're going to be looking at the proposed system and the components that allow the proposed system to operate correctly. We can split this into three different project stages. The first stage being the sensing stage. This is where the data is entered into the system. So in a virtual situation, we have the data entering the system in a form of a file or an Excel file with all the data already on it. In a real life situation, this is where the camera would take a photo of the pill or the force sensor would measure the weight of the pill. In the virtual situation, we're using candies instead of pills to show that our system completely works. Next, we have the data processing stage. It's where the data from the sensors are processed, analyzed, filtered to turn into sensible, understandable information that we can start to split up for the next stage, the sorting stage. This is where our virtual instrument splits this data and understands it and then is able to sort it into the correct jar. In the virtual situation, we use picture rings to show that we understand which pill goes into which jar. So let's start looking at functions. This black box diagram shows material, energy, signal, and the software used that goes into the system and splits it into the final output, the dispensed single sorted pill. First is the force sensor, also a measurement of the weight. Uh, so we take each pill, we measure its weight, see if it's within the acceptable range of the manufacturer. So if it's not within the 95% confidence interval, we understand that that might be an error pill that we do not have on our system, and we might have to put it into the error jar. So then we have a camera sensor. This identifies the size and color of the pill. Finally, there's a photodiode, which understands and counts the exact amount of pills for each jar and that come and go out of the system. So then we sort the pills into the correct container using, in a real life scenario, we would use a servo motor. In this situation, we show with a picture ring which pill is going into which jar.
Filtering can also be seen in our system. A thresholding filter has been used for the identification of the shape from the acquired image. Any value that is not zero but is also not a part of the object is set to zero, allowing for better separation between the actual image of the pill in the shadows or noise of the image. Of course, as in any other system, there are some limitations to our method. Our device has the disadvantage of only sorting one pill in each turn. Moreover, if the images that are acquired are not of very good quality, the proper function of the image processing stage can be severely affected. Moreover, since we are using a filter to identify the shape of the pill, it is very probable that some errors could occur due to the sensitivity of the camera. To further understand the limitations that occur due to the sensors, let's focus on the functions of the sensors and the exact physical and theoretical functions they serve. In the original system, we used 3 sensors and 1 actuator. Starting from the force sensor, it is important to keep in mind that it is used to identify the weight of the pill. The force sensor is a piezoresistive sensor, which means that its resistance is variable based on the pressure that is applied over the sensitive area. The active area is separated from the conductor film by a thin adhesive layer so that the greater the pressure that is applied on the top, the closer the area gets to the conduct of the film, creating variable resistance for the sensor. Since this is the only change in our system, the VI can recognize the change in the incoming voltage, and through different processes, it determines the applied load.
Another sensor that the team originally was supposed to use is the photodiode. This sensor would be exploited for its ability to count the number of passing particles. The method of the diode's operation is based on the absorption of photons that excite the optical fibers in the photodiode and create a voltage to run through the diode to the VI. The photons are sourced by an infrared laser that directly feeds to the diode. As a particle is passing, there is a disturbance in the infrared wave, and there is a brief change to the voltage produced. By counting these disturbances in the VI, the user can find the number of pills that have been sorted. The third sensor our team used was the camera. Firstly, an image is required by the device, that is then duplicated. The first copy is converted to grayscale and is passed through a filter to remove the background and only keep the image of the candy. This is then loaded onto the iMac Detect Shapes VI. This VI has the capacity of identifying whether the shape of the object is a circle, an ellipse, or a rectangle. After the shape of the candy has been determined, the second, non-grayscale duplicate is loaded onto the iMac Color Learn VI. That, based on the region of interest identified by the user, turns the image into an array of different colors. The maximum value from the index of the array is used as the color of the image. This stage requires a lot of calibration based on images of solid colors taken with the same lighting. This is a great source of error, as the lighting can vary significantly. Next in our VI is the rotating servo. The servo consists of a distance motor that can spin to specific angles based on the previous identification of the pill. When the identity of the pill has been determined, the VI sends a voltage signal to the DC motor and makes the disc turn so that the tube ends up in the correct container.
Now, moving on to VI development. I started off by developing a program to identify pills by weight. So there's an input for the weight, which in this case, in this image, is a custom control. If this were a real system, we would use a strain gauge to send weight information, and we would run it through a series of calculations to figure out the weight of the pill. But since we're doing this virtually, it's just easier to use a custom weight or a random number generator. The weight goes to a series of ranges, as you can see in the image, and if the weight fits within the image, then it sends a true signal towards the AND gate, which is added to another true value, which would be coming from the image processing, but since we were just starting with weight, it just came from a constant. This sent it to a conditional statement, so that says if it's true, then send it to an array filled with zeros and then one number or all zeros, and then it sent it to a ring, and the ring selects the image based on the maximum number from the array, in which case it would either be a 0 or it would be one of the numbers that it produced, and each number corresponds to an image. Then we moved on to shapes. First, I just initialized the vision acquisition and sent it an image path, so a file with an image in it, and then it takes that image and converts it into a grayscale image and then sends it to a bunch of separate VIs that detect different shapes. That was the first phase of shape detection. The detect shapes VI wasn't very accurate, so it was good at detecting circles and ellipses. However, when detecting rectangles, it really didn't like the edges of the image that we were giving it. So I gave it a conditional that it either has to detect a rectangle or it doesn't detect circles or ellipses, and that also counts as a rectangle. Then moving on to color processing, I had to make a copy of the image so that software didn't confuse it with the grayscale image. So that's what happens there first. And then it goes into a VI called Color Learn VI. You can see there's a region of interest that I've selected. In this case, it's a pixel, but in the final VI, you'll see that it's actually it's a rectangle that we've selected that will only take the color values from there. And then what Color Learn does is it figures out it returns a one-dimensional array of all color values, and whichever color value is the highest, so each color is indexed. So for example, red is index 2, and so if red has the maximum value, then the max index would be 2, And so you can see in this case red was actually 1, white index was 15, blue index was 11. So we search the array for the maximum index and compare it to the known indexes of each color, and then that sends a signal whether or not it's red, blue, or white. After all of that, we combined them all into one, and you can see the final VI looks something like this. So over on the right, we have an animation of the sorting mechanism, the strain gauge in the middle, and the image on the far left. This is the final block diagram. So on the right, we have zeros initializing the program, the vision acquisition here, and then it goes to the detect shapes. You can see some changes have been made just for accuracy purposes. And then up to the color processing. Again, the region of interest was changed to a rectangle. Everything else pretty much stayed the same. These were all then connected to replace the true constants in the AND statements. And then those go back over to the conditionals, and the same thing happens. And as you can see, there's also counters. So that's what the initializing the shift register. So now we'll move on to test cases. We'll start with test case number 1. In this test case, we have to confirm that the system can input any number of one type of pill and identify correctly and count up on a counter. We'll start off, we'll set the sorting speed at about 5 seconds. We'll open up the file, we'll select a red skittle. We'll go down and we're just going to confirm that everything is set normally, so it hasn't identified a color. We're going to put in a custom weight, which is 1.1, which should be the weight of a skittle. Then you can see red skittles off, everything's set to 0, and everything's at normal. So we'll run the system and we'll see what it does. So as you can see, it's identified it as red, which is correct. It has selected the weight as 1.1, which we wanted. You can see that the number of skittles is going up as it loops, and it's correctly identified it as a red skittle. So this confirms that test case number 1 works. So for test case number 2, we need to confirm that the system can take any number of pills and that they can recognize the changes that occur in the shape and the color, and that they will be sorted into the appropriate container. Some limitations with the virtual version of this is the fact that the weight isn't being taken. So in the demonstration, I'm going to input a custom weight that follows each pill. We enter the file folder to confirm there's 5 different kinds of pills. It's going to be sorted at about 5 seconds. It hasn't identified any colors, and we're going to start off with the first pill is a weight of 1.1 grams. So we'll have to change that as we go though. So you can see again, I just had to turn off the red skittle light, but everything's good here. So we'll start running the system now. You can see it's identified it correctly as blue. Its correct weight range, it's identified it as a blue Smartie. So now you can see since it didn't fit the correct weight, it's gone to the error jar. It's identified a red skittle correctly since red skittles fit in that weight class. It's now correctly, it's going to go to a Tic Tac with a weight of 0.5. It's identified the Tic Tac correctly. Now we'll go to a weight of 1.4 for gum. You can see it's gum, it's white, 1.4, it's identified it correctly as gum. Now we'll go to a weight of 5 for the Starburst. You can see it's Starburst, it's red, it's a rectangle, it's identified it correctly as Starburst. And as you can see, there's 1 of each one. So there's 1 Starburst, 1 gum, 1 Smartie, 1 Skittle, and 1 Tic Tac. So this confirms that the system can correctly identify 5 different kinds of pills of random amounts. Moving on to test case number 3, we need to confirm that if a random pill is loaded into the system but is not included in our database of pills, then the system will sort it out and create a discard jar for the unknown pill. So you can see we're going to go in and it's a green Skittle. Green Skittle isn't part of our system at all. There's no green indicator. There's no green jar. So we're going to turn off the custom weight and turn on random weight. So we'll run the system and you'll see it doesn't identify any of the colors because it's not one of those colors. It has selected some random weight and it fills into the error jar. It doesn't identify it as one of our pills. So this confirms that test case number 3 works. If there's a random pill in the system, it will sort it out and will send it to the error jar.
In conclusion, the team has been able to create a VI that can successfully sort pills based on the shape, size, color, and weight. The pills are sorted into containers, and if the reading for the weight is not within the acceptable intervals, they are rejected, giving the user information about the purity on the substance.